All right, welcome back to the final part of the session 3 on multi-level perspectives. And in part 1 and part 2, I have motivated why levels of analyses matter. In part 2, we tried to motivate what does that multi-level model look like and what do we gain by doing so, what are the types of questions we can answer. And in number 3, I want to sort of take that a much sort of broader perspective. As you saw in part 2, I narrowed my example to just thinking about place and individuals. But we can have a much broader perspective, and I want to sort of expand your horizon around, what a multi-level data structures are and how frequently we encounter them in the population. So, an obvious question for this session is, what generates a multi-level data? So one answer to that could be that the real world generates them. So the world out there does not look like a simple random sample. There is a structure to it. Populations are structured. In some instances, those structures are what one might call as a naturally occurring hierarchy. Okay, they occur in the population. That's how life is structured in the population. Some examples of those, for example, if you're studying children and if you're studying whether their health outcome or their academic achievement, and the way you get to study children, the most efficient way is to go to the schools, because that's the most efficient way to interview children. Right? But schools are not just a way of getting to children. Schools are part of children's lives. The classrooms that they spend, they're part of their lives. So there is a structure. So when I see a data on kids that's generated from interviewing them in schools and classrooms, and the analyst completely ignores that aspect of schools and classes, to me that's like completely stripping off that individual from the data structure that actually produced them. Okay. So you can take a very substantive approach that whatever outcome you're going to observe for these individuals, it's coming from a population of which they are part. So children are, the definition of a child population will include or should include or may include the classrooms that they go to, the population of the classroom, the population of the schools. Similarly, if you're interested, if you're a healthcare healthcare researcher or health policy researchers, wanting to understand patient quality, again, patients are part of a distinct population and they're exposed to that. They're part of a clinic they regularly visit those clinics. Clinics in turn tends to be part of health authorities. In political geography, in electoral geography, you can think about the polling district and the constituencies as providing the context. These are naturally occurring hierarchy. Within social epidemiology, we have spent a lot of time and a lot of research around individuals nested within neighborhoods and cities and so on. So to some extent, you could argue that the multi-level data is generated by that's how world is structured. At least one way of looking at that world is to apply that lens of that it exists out there. Of course, a design can also generate multi-level data. So if you look at this slide, you can see that in the graph A, the most efficient way of getting to an individual is not by simple random sample, but by multi-stage sampling. So if you look at the graph A, that would be an example of a simple random sample. I take an area and then I go through my telephone book and I pick up every 10th person, or go through my electoral polling list and pick up every 10th household or something like that. That would give me a random sample whose distribution should look pretty random, as you can see. Or increasingly, a lot of the survey data that we often have a multi-stage sampling design. And the simplest form of multi-stage sampling design would be a two-stage sample. So what people would do, the survey statisticians, they would demarcate that larger area into 4 primary sampling units. So, and then within each primary sampling unit, you then draw a clustered sample. So when you do this is very efficient. It's very efficient. However, it ends up violating one of the principles, one of the assumptions of the regression models, which is that the data should not be correlated. But when you draw a sample like this, you generate a clustered sample. You generate a correlated data because you're drawing information from the same area and it's a clustered sample. So essentially a multi-level data, if someone asks you, what characterizes a multi-level data? Well, it's characterized by, it's a correlated data. It's a dependent data. You observe for me, if another individual is drawn from the same classroom, same school, same area, they would be more alike than what one would have observed if they were purely being drawn from a simple random sample. So multi-level data, either the real world is clustered and correlated, or your sampling design generates that. So what if there's a correlated data? Well, there's a substantive reason why we should care about it. And number one, we care about that because individuals living in the same neighborhood may be influenced by some shared characteristics of the neighborhood, right? So this notion of the shared exposure. So if that sharing is what induces correlation, the reason that two individuals have similar kind of outcomes is because they're both exposed to the same exposure. So if you're thinking about children and their academic achievement in a classroom, they're both exposed to the same teacher. Of course, they come with very different potentials and capabilities and so on, but they're also exposed to the same exposure, these two students compared to two students from a different classroom. So that's the idea that individuals coming from the same grouping will be are exposed to some shared exposure. So that's one substantive reason why we care about a correlated data. And number two is empirical, that it's useful to know to what extent individuals are correlated in a particular group. So higher the correlation, it tells you that it's not really individuals, it's something happening at the group level that's making everyone the same, as opposed to, so it's good, it's a useful empirical information for further research or for policy as to which level you want to focus. Higher the correlation, you're saying groups are more important. Lower the correlation, you're saying individuals are more important. So it's useful to know empirically what's the quantity, what's the degree of similarity. There are, of course, technical reasons as well. And the technical reasons is, as I've already alluded to, individuals drawn from a clustered sample or from a multi-state sampling design can be expected to be more alike than a random sample. And what's the implication of that? The one implication is that you now do not have as much level 1 information as it appears. What do I mean by that? Let's say I sampled 1,000 kids from 10 schools. If I sampled 1,000 kids from 10 schools, let's say 100 kids in each school, and they all have exactly the same BMI within a school, right? So even though I measured 1,000 kids, they all seem to have about the same BMI. In that case, my real sample size is not 1,000, it's 10. Because the potential variation that I'm observing is only between schools, not between individuals. So as the amount of clustering, as the amount of correlation between observations increases, the level 1, the child level information, the true effective sample size goes down. And why is that important? Well, all inferential test relies on the assumption of independence of observations. And if your observations are correlated or dependent, you're violating that assumption. And and what does that lead to? It leads to the incorrect estimates of the precision. You get much lower standard errors, and mainly you end up committing the type 1 error. So you are more likely to find a relationship or a difference where actually none exists. So both for substantive reason and for technical reasons, there's a need to use the clustering or correlated data matters. So to sort of just build a little bit more on that aspect of, what is a multi-level data? You've already sort of gotten some sense of that. That it's a clustered data, but how does it look like? So this is one way of looking at it as sort of a 2x2 grid of exposure by outcome. And I have separated the grids within the columns and the rows by a small x and a capital X, the rows. So that's this exposure, the small x is an exposure measured at the individual level, capital X at the place level, and a small y is an outcome measured at the individual level, and a capital Y outcome measured at the ecological level. So the traditional risk factor study is correlating some individual level outcome to some individual level risk factor by ignoring the ecology of any form. So what you might get with the Framingham Heart study, a lot of analysis are essentially that. Ansel Keys' design was this: even though he collected data at the individual level, he aggregated them to the ecological level. So the capital Y, the mean rates of blood, the mean blood pressure, the mean BMI, the mean levels of serum cholesterol, and the X is also aggregated, the fat consumption, the mean level of fat consumption. So that's a sort of the, and as we've already seen in the part 1, that doing only ecological or the individual is problematic. Especially, and where the multi-level comes is that both matter. So you have individual level outcome. Usually a multi-level data would be a data with individual level outcome variable. It would often have an ecological exposure variable, the capital X, and often also a lot of individual level X variables as covariates or as other variables that a researcher may be interested in. So that's how we define a multi-level data. I'm now in this sort of the final part. I'm just sort of going to show you 4 or 5 typologies of multi-level data structures, just sort of as a representation to basically argue the case that a lot of the data structures that we encounter in the population is a special case of multi-level, not just individuals in neighborhoods or kids in schools, but we can more generally apply that perspective to a whole range of data, a whole range of research questions as well as structures that exist in the population. So a simple hierarchic structure that we've largely been talking about is this notion of individuals nested in place. So in this particular slide, you can see that the hierarchy aspect here, and what defines that this 2-level hierarchical structure is the following. There are lots more level 1 units nested within fewer level 2 units. Indeed, that's what makes it a hierarchy. You know, a hierarchy is like that, a lot of units below and fewer as you go above. We also make an assumption within the multi-level model that the lower level unit within hierarchical models, that the lower level unit is nested within one and only one higher level unit. So if you look at that person 1 in place 1 in that picture, you would see that there is no arrow going from person 1 to place 2. You know, maybe place 2 is just next to place 1, so there is no reason why place 2 may not influence that person. I'll come to that towards the end of in another 5 minutes, but in this particular specification, simplest one that we can think about is a hierarchic specification where we nail the individual to only one context about them. And in general, in multi-level models, we view that there are 2 units of analysis here. So we have people at the level 1 and places at level 2, and the expectation is that those 3 places or 30 places that you may have in your sample is one realization from the population of places that's possible. Similarly, those 5 or 6 individuals that are shown in this particular slide are one realization. But you're not interested in those 6 individuals, you're interested in the population from which they're drawn. You want to make inferences to the population of those individuals, and you want to make inferences to the population of places of which you have one sample. We can extend that and a code that I really like, which is that once you know that hierarchies exist, you see them everywhere. This is a code by one of the pioneers in the multi-level model, Ita Kraft and Van de Leeuw, in one of their books. And one might argue that every data structure is a special case of multi-level. So what do I mean by that? Well, let's take another thing that structures data, time. So far I talked about place that can structure the data. Let's look at the time, something that the in-depth cites a lot of the data do have, which is you follow the same individuals over time, and that generates a multi-level data structure. So if you take this example that you can see here, at level 1 you have time, level 2 you have individuals, and then I can further bring in the places where they lived or are living at level 3. So if you think about the person 1 in place 1 has been followed in 1990, 91, 92, 93, but person 2 in place 1, we somehow could not get this guy, which is normal, you know, in a longitudinal panel study. There's always an imbalance, and that's not a problem. That's something that exists in the population. Imbalance is often is encountered in the population, but you can clearly see that time, a panel is just a special case of multi-level where time, repeated measurements on the same individual is nested within the individual, and you can further extend that to places. A variant of that time can also be when you don't measure the same individual, but you measure the same place. So this is the idea of a repeated cross-sectional design. So time can be structured in 2 ways. Am I repeatedly measuring the individual, the same individual, or am I repeatedly measuring the same place, but a different individual at every time? And that's a lot of the data sets. A lot of the data sets have this design, and again it can be quite usefully cast as a multi-level design. It's a multi-level data structure of individuals nested in time. And for example, in this particular graph you can see that place 1 is repeatedly measured in 92 and 93, but in 92 and 93 we don't know, or they are completely different cohort of individuals. And what this kind of a design allows us to answer is being able to sort of think about, you know, changing geographies of mortality conditional on the changing composition, because at every time I can control for who's in that place at that time. So when I'm making assessments about the changes in places, the trajectory of the changes in places, I can control for how the composition has changed. And that's sort of quite a useful application of this kind of a design to multi-level models. You can also cast a situation where you have multiple outcomes, you know, not multiple exposures. That's pretty common. That's just multiple regression. But multivariate, in the strict statistical sense, means multiple outcomes. So when you're interested in more than one outcome, and all these outcomes are correlated because they're coming from the same individual, and your interest is in understanding the correlation amongst these 4 outcomes at the individual level and at the place level. So how likely is an individual who smokes, is also likely to drink, is also likely to have a poor diet and poor physical sedentary activities, and same thing you can do at the place level. So you can sort of think, is the geography of smoking the same as the geography of drinking versus sedentary behavior or diet. So this notion of, if you are anticipating that the different outcomes are correlated, not in any directional way, it's not that one causes the other, but they co-occur. They are correlated, and you can model that. You can cast that problem quite flexibly as a multi-level problem and gain a lot of advantages. Those were some examples of hierarchical structures. You know, still, if you look at all the pictures before, the lower level unit is nested within only one higher level unit. But life is not hierarchical. Life can be non-hierarchical, it can be cross-nesting. So what I'm showing here is a case. Let's think about a situation where you're interested in studying children, and let's say their BMI, and you believe that a child's BMI is a function of not only their own characteristics, but also the school they go to and the neighborhood where they live. And you want to analyze the relative influence of the schools and neighborhood. But schools and neighborhood don't nest. They're not a neat hierarchy. So for example, in this particular tabular format, what I've shown is that in a given neighborhood, kids can go to different schools, or in any given school, kids can come from different neighborhoods. Okay. And when I analyze this data as a simple hierarchical model of schools separately with kids, neighborhoods separately with kids, I would end up overestimating or underestimating the effect of one or the other. So it is really important to think about there are multiple contexts that can influence behaviors or outcomes. And in this case, just one example of what we call as a cross-nested or a cross-classified sort of a framework. So it's non-hierarchical, so not all hierarchy, and hence the term multi-level and not just hierarchical models, because there are non-hierarchical structures that are also important to be considered in analyses. And extending that is this general philosophy within which the multi-level models have been developing, and they are being sort of discussed about, is this a broader idea of realistic complexity. We don't want to make analysis unnecessarily complex when actually it is quite simple. That's not the goal here. The goal is really to sort of, there are certain things, certain assumptions that we make about our current simple models are just not realistic assumptions. And some of the things that do occur in the populations is how things get structured. So for example, what I have shown here is a design where you're observing the same individual over time, let's say 2 times in this case. But over that study period that you have from time 1 to time 2, individuals need not be nailed to one place. They are free to move. These are not institutional populations. They can move. And that part of mobility is quite normal. It should be anticipated in the analysis. It's not an aftermath of simplifying that assumption, but this is something that we can anticipate. People might move during that study period. So for example, individual number 25, living in neighborhood 1, sometime during that study period, moved from neighborhood 1 to neighborhood 25. How do you account for that? So this is making it non-hierarchical again. And what you see in those dashed lines, the 0.2 and 0.8, are weight matrices that we can apply. So for example, we could say that individual 25 of the total study period only spent 20% in neighborhood 1, but spent 80% in neighborhood 25. So when you're aligning your exposures measured at the neighborhood level, you want to account for that weighting, because otherwise you're misclassifying that individual to a different environment. So this notion, the fact that people move is quite normal. And we need to accommodate that in our analysis. And multi-level models, again, with this kind of data structures, are very, very easily implementable within those multi-level frameworks. So to wrap up, the take-home message from this module, from this part 3, is that multi-level perspectives are very appropriate when these 3 things are of importance to the researchers. Number 1, you find that the observations, or you anticipate that the observations that you are analyzing, that you plan to analyze, are correlated. And they're correlated because of some shared exposure. And that shared exposure could be due to geography, could be due to institutions, could be due to history, could be due to social processes. Number 2, if you believe that the cause, it's not one risk factor at a time. It's multiple risk factors and at multiple levels. So if you believe that the causal processes that influences outcome in health outcomes and behaviors, they operate simultaneously at multiple levels. If that's the conceptual view, which is a main cornerstone of the social determinants of health perspective, then a multi-level way of setting up your analysis is the most appropriate way. And finally, that has not been exploited as much within multi-level applications is this appreciation of heterogeneity. Often, if you read papers, or the best paper or the worst paper, all they report is one effect. This is the effect of X on Y. There's no probing, there's no question of is that association really constant everywhere all the time, or is there a heterogeneity? And in some designs, like the in-depth design, where we have multiple sides, we can model, we can try to answer that heterogeneity to see if the same association is found in every place. And if not, it begs further scrutiny. It may want us to go back to the drawing board about thinking about the question differently. It raises new question, and that's a sort of the huge benefit of taking a multi-level perspective. It's in asking newer questions in addition to answering the older questions in a more technically superior way. Thank you.